So in this video we're going to have a look at sequences and how we can identify them and write a recursive rule. So a sequence in mathematics is a string of objects such as numbers that follow a particular pattern or rule. So when we look at a sequence of numbers, for example, each individual element or each number in a sequence is called a term. So in example 1 we're going to consider the sequence 3, 7, 11, 15 and 19. So before we jump in, we can take a look at the pattern that's occurring here. And as we go from each term, ideally term 1 being our first term, to term 2, to term 3, to term 4 and so on, we can see that we are adding 4 each time. So our pattern is adding 4 to the previous term. With our notation, to show that what's happening, we could write each term with its notation. So capital T for term and a subscript 1 to say we're talking about term 1 and its value is 3. Term 2 has a value of 7. And for example, term 6 has a value of 23 because we're going to add 4 to term 5. Taking this a little bit further, we can notice that we've got a particular type of sequence happening here because we are simply just adding by the same value each time. So we call this an arithmetic progression. We often call A as the first term instead of writing T subscript 1. And if we've got a constant difference, we use the letter D. And we'll see some more of that shortly. What we can do once we know a sequence is complete some calculations. We can ask you, what is term 8? Well, simply we could continue this on. We know what term 6 is. We can work out term 7 is going to be 27. Therefore, term 8 will be 4 more than term 7, 31. Term 2 plus term 3 is simply going to be 7 plus 11. That will give us 18. 3 lots of term 4 means 3 lots of the value of term 4. The value of term 4 is 15, so that's going to give us 3 lots of 15 is 45. And 2 lots of the difference between term 4, which is 15, and term 2, which is 7, simply means 2 lots of 8, which is 16. So to defining each term in a sequence, we can use its values to calculate. What we can also do with a sequence, when we see a pattern, is we can write what we call a recursive rule to summarize what's happening. This type of rule is used to find the next term if the previous term or terms are known. So we're looking at how a pattern recurs or repeats. So let's go back to example 1. We had the numbers 3, 7, 11, 15 and 19 and this continued. We could see to get from term 1 to term 2, we simply took term 1 and added 4 and that's how we got 7. To find term 3, we simply took term 2 and added 4 to get 11. So we're taking, if it was term 2, we're taking the previous term. For term 3, we're taking term 2, the previous term. So to find term 10, for example, we would need to know term 9 and then we would add 4 to it. So to write a recursive rule, we're simply going to say, to find any term, we take the previous term, so the previous to n is n take 1, and we're going to add 4. What we must do is define what the first value of our sequence is so that we've got a starting point. So this is very, very important. What we could also do is start with Tn plus 1. To find the next term from term n, we would need term n and we would add 4 to it, where the first term is 3. What we're trying to do is identify the link between, if we want to find a term, we must use the previous term. we want to find term n plus 1, we must know the previous term n. Let's have a look at our second example. Let's consider the sequence of 3, 7, 15, 31 and 63. This one's a little bit different. By examining this pattern, we're not just adding on consistently, because we've got add 4, add 8, add 16. So that tells me something else is happening. In fact, what we're doing is multiplying by 2, then adding 1 to get to the next term. So we can see 3 times 2 is 6, plus 1 is 7. 7 times 2 is 14, plus 1 is 15. But we're doing this to the previous term, so we can get the next term. So we've got the first 5 terms. So to find term 6, I would simply say 63 times 2, then plus 1. And that would give us our value of 127. So let's use some notation. Term 1 is equal to 3. We also gave that the value of A. Term 2 is simply going to be 2 lots of 3 plus 1. That's 7. If we continued this, we could write a recursive rule that says to find term n, it would be the previous term, which would be n take 1, times 2, and then add 1. But we must have a starting term. Our first term is 3. Or we could write this recursive rule as starting with tn plus 1 to get the next term. This is why n plus 1 is often used. We must use a current term, which would be tn. We're going to times it by 2, and we're going to add 1, where our first term is 3. It doesn't matter what notation that we use for our recursive rule, as long as it links between the value at the front to its previous term. Our calculators or our class pad tends to use the n plus 1 and n example, which is our second recursive rule there. A particular sequence where we're simply just adding on a constant number to the previous term all the time is called an arithmetic progression. This is often summarized as an AP. So an arithmetic progression is a sequence where each term is obtained by adding a constant number to the previous term. So in our third example, we've got 27, 34, 41, 48, and continuing. So term 1 is 27, term 2 is 34, term 3 and term 4. And we can see our pattern straight away is adding 7 to the previous term. That's our pattern. So we have that idea of D, a constant difference. So in this case, our D value is 7, and our A value, our first term, is 27. So we can write a recursive rule here that says to find any term or the next term, we must know the previous term, and we're going to add 7. But we must have a starting term, so term 1 is 27. As I've said previously, we could say that A is 27 and D is 7. So now that we've identified the pattern in our arithmetic progression, adding on 7 as that constant difference, so adding 7 to the previous term, and we've got our lovely recursive rule which says, how can I use the previous term to get the next term to show that recurring nature? So we can then use this to find term 5. Now it's quite easy to find term 5 if we know term 4, in which we do. So we can simply say 48 plus 7 is 55. Now to find term 8, we could continue our sequence saying 55 and adding 7 more on. That's going to be 62 and then 69 and then 76. So we could get to term 8 that way. It might, however, be easy to think about the fact that to go from term 5 to term 8, we've had to add on 3 lots of that 7 that's being added on each time. So we could also think about term 8 as 55 at term 5 plus 3 lots of that difference that we've had to do to get to term 6, 7 and then 8. And that would help us arrive at 76. And that's the same thing as for trying to find term 20. Ideally, using our recursive rule, we would want to add 7 onto term 19, but unfortunately we don't know term 19. So we have to try and be a little bit more flexible with our options. We could use the same idea that we used for term 8. Perhaps we could go from term 5 again at 55 and add on 15 lots of that positive 7. That's our difference that's going to happen. So if we do that and add on 15 lots of that difference, we do arrive at 162, which is term 20. But that's really stretching our ideas because we don't have a general rule at this point. So in summarising, for an arithmetic progression knowing that we have a constant difference between the terms, we can generalize that recursive rule, that recurring nature. It says, okay, if we want to find the next term, tn plus 1, we must know the previous term, tn, where we're going to add on this constant difference. But we must have term 1, which we've given the notation of a, our first term. We could also write this if we had tn being the next term, then tn take 1 would be the previous. We're still adding that constant difference on, where our first term would still be a. So I've now got 4 questions for you to have a go at. So I'd like you to pause the video and take a look at these and have a go at completing them, and then come back and check your solutions.